are really, really fortunate to have Russ Schnell come to speak to us today. Russ Schnell is an eminent scientist in matters of climate, and this is a big topic for all of us now, we know. And so Russ was coming up to Red Deer and central Alberta. He's originally from Castor, so he's actually making a home visit these days, and said, is there any chance that we could have an audience and he would be prepared to speak? So we are so fortunate today to have Russ come to speak with us and share with us some of his thoughts and some of the information that he has as one of the eminent climatologists of the current time. Russ has a connection with Red Deer because when he was going to university and graduating, one of his very first jobs was at Red Deer in the atmospheric. He can tell you much more than I can. I wouldn't begin to. He's given me some notes here, but I'm not onto the words, and I don't think you would be either. You'd need Russ to interpret the jobs he did. But anyway, some of the cloud seeding that has been done here to suppress hail, and also the fact that Russ, in his research, discovered that little bits of organic matter form at the will have moisture gather around them and form either raindrops, hailstones, or snowflakes. And Russ has adapted that into the development of making artificial snow. Now that's my version of it. He has a much more complicated version and a much more scientific version. But this is the man we are privileged to hear today. And during some of the climatological research that he has done, in his work in 92 countries in the world, and has just recently retired from the National Oceanic and Atmospheric Administration in Boulder, Colorado. I think that perhaps the pinnacle of his research and success and so on was when he shared a Nobel Peace Prize with Al Gore in 2007. And when I met him, I said, "You are the very first Nobel Peace Prize winner I have ever met and seen in the flesh." So we have amongst us someone who has a very, very powerful message for us and a very optimistic message. Russ is a very optimistic person. So I just want to also mention that I said Russ is from Castor. So by way of the electronic world that we live in, the Castor Public Library is receiving this broadcast, and the Paint Earth Lodge at Castor is also online and joining us in this audience. So I would like you to give a warm welcome to Russ Schnell. Russ.
Let's do a mic check. At the back, can you hear me?
Oh yeah.
Okay. So we're going to digress for a minute, and I'm going to pass around something I'd like you to look at and tell me what this is. But only people who I haven't already told, you can't do it. And the person who guesses it right gets a $2 bill. Pass it around. It's heavy. That's the small one. This big one weighs 28 pounds. And I'm not going to pass it around, but it's the same. It comes from the same. No, it's too heavy. You drop it. And you guess what that is. A $2 bill to whoever gets it right. And no cheating. Okay. You've all seen a globe like this. They all hang at 23 degrees, but have you ever turned it around and looked at it like this? You don't see much land, do you? There's an awful lot of water in the world. And keep that in mind, because that's very important in climate. Now, I'm going to put my hand over Red Deer and bring it down. I want you all to vote when you think I'm at the top of the world's atmosphere. How thick is the world's atmosphere? Here's the globe. How thick do you think the world's atmosphere is? And everybody should vote. It's as thick, relative to the size of the globe, as this piece of plastic. No, that's right. When you fly in an airplane at 35,000 feet, 95% of the world's air is beneath you. Think about that for a minute. Oh, it's not much air. So whatever we do to it mixes around. So we can screw up the atmosphere really fast by putting stuff into it. Keep that in mind. There's not much air, and it's very thin. Now, when most people in the world, you ask them, what direction does the wind blow? Here, on average, here we say west, northwest. Okay, go across the whole US, come to Europe, what do they say? Oh, west, northwest. You go across Russia, what do they say? Oh, west, northwest. Say to Japan, west, northwest. The air goes around in the northern hemisphere where a lot of people live. If you put up some pollution or a balloon here in the US or Canada, it'll go around the earth and come back in 10 days or less. The air moves around. And I like to say we all live in somebody else's sewer. Yeah. That's basically what happens. We get our sewer from China. The US gives it to Europe. Europe gives it to Russia. Russia gives it to Japan. It just keeps going around. It gets diluted, of course. But it's a big circle. So keep that in mind. When you see a big diesel truck shifting gears, grung, grung, big black cloud, and then it disappears, you think it's gone? No way. It's just being diluted. And I published a paper about 15, 20 years ago measuring right on the South Pole, and the black carbon is there, and you can see it coming. It mixes around the world. And then in the Arctic, it sits on the ice and helps melt the ice, the black. So whatever we do doesn't just stay local, and whatever other people do doesn't stay local. You've got to keep that in mind. We're all in this together. So today we're going to look at data that shows you, is that still working? We're going to show you data of how the atmosphere is changing. The air that you breathe is very different than what your grandparents breathe, the composition. And it's very different than what your children and grandchildren will breathe. Now, how do we know these things? Well, I'm going to ask you a couple questions first. You know how thick the Earth's atmosphere is now. It's very thin. How many kilos of CO2 are produced by burning 1 kilo of gasoline? If you can read the fine print, you can see. Three times as much. Think about that. All of the coal, oil, natural gas we burn produces carbon dioxide. And it produces more in weight than what you're burning. And in oil and gas, it's 3 times as much, because you have this long chain of carbon with hydrogens on it, and then you take a big oxygen molecule, which is 16 times heavier, and it kicks off the hydrogen, and that's where you get your energy. But now you've got this big, heavy CO2 molecule on there. So the weight of it. And where does that CO2 go? Up. Everywhere. It mixes around in that very thin atmosphere. And how long does it stay in the atmosphere? If you can read the small print? 100 to 1,000 years. Okay, that's a long time, isn't it? Yeah. Now, why do we care? Molecules of CO2 are very small, and they're very small concentration, but they're increasing in the atmosphere. Why do we care? In the red, carbon dioxide holds heat in the atmosphere just like a thin down blanket. So the atmosphere is heated from below. It's not heated from above. So the sunlight comes, boom, hits the ocean and the ground, warms them up, and then that heat, you see it in the summer, all of those heat vibrate. Then the atmosphere holds that heat. And it's held by 3 molecules generally, carbon dioxide, methane, and nitrous oxide. And it acts just like feathers in a feather bed. It holds the heat. When you're in a cold room and you get in a nice feather, under a blanket with a feather bed, you warm it up. It's not the feathers that are warming you, it's your heat that's being held, and that's exactly the same as the atmosphere is. The carbon dioxide molecules are little down feathers, and we're adding a lot of it. So you add a lot of down feathers, what's going to happen? Right, the ground is going to warm up, the ocean are going to warm up because you've got more heat in the atmosphere. Now, let's look at what we know about that. I worked for an organization for 45 years that measured everything like this all around the world. And we have stations, manned stations, and stations on the ground. And you can see here, we have about 170 locations where we're measuring what's in the air. And you say, well, how do you do that? Well, a couple of ways. One of them is we have manned stations. We have manned stations at a lot of interesting places. Okay, my pointer isn't working, but don't worry about it. We have them in Mauna Loa, Hawaii, which is our most important station, Summit, Greenland, right on the South Pole, in the American Samoa. We closed Trinidad Head recently, in Point Barrow, Alaska, where people live and run instruments, huge numbers of instruments, all day long, all night long, every day, every hour of the year, measuring what's in the atmosphere. And we measure a minimum of 250 different things at these stations, and even more when I'll show you in the next slide. Oh no, let's digress for a minute. Russia, as you look on this, is a big country, isn't it? 11 time zones across Russia, and they have almost all of the Arctic land is in Russia. So, before all of the current problems developed in Russia and Ukraine, the U.S. And NOAA and NSF opened 2 stations in Russia. I've been to Russia many times, and in the Arctic, and we opened up a station in Cherskate, right on the coast. That used to be a prison colony for dissidents, and they still got all of the big fences and all of the concentration camp stuff is still there. And then we opened another one at Tixi. Tixi is another location. So we had 2 beautiful stations operating in Russia, getting a lot of data. It's very important, as I'll show you later on. But there's the station. It's a little blurred, but we paid a couple million to a mafia Russian group to build this station. And then we outfitted it and everything. And then when it was time to open the station, who should come but to open it but Putin. There he is. But we were there, but we were not allowed to be within 10 miles of him. That's a picture of me on the other side talking to some other people. They locked us up 10 miles away until he came and went out of security. So we didn't see him, we didn't get to shake his hand or anything. He probably didn't even know we were in the area. But anyway, an interesting event. But now, about a year ago, they stopped sending the data from the stations, and we were not allowed to even, if we could get it, we couldn't even look at it. So all of that investment, all of that data, all of the measurements, maybe someday we'll get it back. But
well, they might be using it.
They might, but they might not.
Yeah.
But they're not telling us about it, and unless the rest of the world knows about it, doesn't help us much. You know?
Yeah.
So how do we measure air around the world? You put it in bottles, like this. See this over here? There's 4 bottles there. At 70 to 100 locations every Tuesday morning, those bottles are filled at different places on Earth. And you saw in the earlier, all of those red dots, that's where this is done. It takes 1 week to learn how to fill a bottle of air. Because if you have cologne on, if you smoke, if you fart, if you cough anywhere near it, you screw up the measurements. So these bottles are filled with a little pumping system. You load 2 bottles in, and then it's in a pump, and then there's a little fishing pole goes up and holds the air line up, and then you run away, and it pumps it for half an hour and fills the bottles, 2 bottles. See the green and the red? And all these bottles are mated. They always go together. And when we analyze what's in there, we can look in there and figure out at least 80 different species. And we measure it in a part per trillion. How is that? What's a part per trillion? That's a small number, isn't it?
Yeah.
Let me give you an illustration. If I pack up silver dollars, as high as me and a little higher, and 6 feet wide, and I make a wall from Edmonton to Calgary, you have 1 trillion silver dollars in there. If you scratch one of those silver dollars, we will tell you in an analogy exactly where you put it in that 200 miles and what side you scratched it on 99 times out of 100. So we can measure one molecule of air coming out of China and tell what's going on, and I'll show you what we've done some there. So there's a huge infrastructure built to measure the air around the world. And when you paint a house, you have this nice liquid paint, and then it dries up. Great, but what dried up? There was a chemical in there.
Yeah.
It used to be a bad chemical, now it's mostly water, but it goes up into the air and it goes around the world. And we can measure that. And we have a joke. We say if all the Chinese people one day ate beans, we could tell you how many tons they ate 10 days later, just looking at the methane. And it's almost true. Almost, but not quite. Anyway, these bottles come. We have 18,000 of these in motion any day on Earth, coming and going. And each of them take about 2 months to go out, get filled, come back, be analyzed, cleaned, and go back out again. And if the two don't agree exactly, and they're both done at the same time, that means somehow they were contaminated, and we can't use the data. And they have to agree. So there's a huge amount of calibration it takes to do this. See all these tanks? Those are calibration tanks. They have in them a certain species and a certain amount of gas. And when you do an analysis, you look at, say you're going to look at methane or hydrocarbon, something, you look at it in one bottle, and then you go and sniff the calibration gas. And then you go back and look at it. And they've got to agree. And then we've got to know that that's correct. Otherwise, we have to throw it out. And our data then is made available often within the day. And everybody trusts it because we're very transparent. We show them the calibration, we show them the measurement, we show them our screw-ups, we show them when we screw up and stuff like that, and then they trust us. And you'll see where this comes important a little bit later. 7,000 tanks like that we have. And we're making new ones all the time, calibrating, because we want to know the measurements that we made in the 1960s are as good as they are today, and that they can be compared to another 50 years from now. They'll look at that data and say, okay, we know that's valid because we can trace back through all of the calibrations, and it's a valid number. And you'll see how that plays out in a little bit here. I'm talking a little faster than I normally do, but bear with me. So let's look at some of the data. This is carbon dioxide, years along the bottom, concentrations up on the left. And you can see that carbon dioxide is going up steadily. In 1960, most of you here were born before that, and look, it's going up and up, and it's going up faster and faster and faster. If you drew a straight line, it would go over here. But you see, we're putting out more and more and more CO2 as we have more people and we burn more fossil fuel and our economies go up. We burn a lot of fuel. So you can see it, and it just keeps going. And each of these, remember, this up and down is annual cycle. In the spring, or in the summer, the vegetation on Earth sucks the CO2 out. Vegetation only grows on two things: carbon dioxide and water, driven by sunlight. So all of the vegetation, the grass, the crops in the springtime, when it starts, they just sucks all the CO2 out of the air, and that's why it goes down. Then in the fall, vegetation stops growing, and you burn more fossil fuel, and it goes up. And each year, the extra fossil fuel you're burning is that little increase. Keeps going up and up and up and up and up and up and up, just this big saw like this. And it's going up faster and faster all the time. So all of these molecules are feathers in this big down blanket that's in the atmosphere. The second most important gas is methane. Methane is produced, is natural gas is methane basically, but also methane is produced by anaerobic decomposition of plants. And like in South America in the Amazon basin, you have huge amounts of tree leaves that drop into the water because there's a lot of water in the basin, and then anaerobic combustion releases methane. Also, in the Arctic, there's a lot of permafrost. That permafrost, when it decays, has a lot of methane. There's more methane in the permafrost in Canada and Russia than there is all the oil and gas that we've ever noticed. Keep that in mind. Huge. And as permafrost starts to melt, what's going to happen? It's going to come up. Then there's a tipping point. If we get too warm in the Arctic, it's going to get too much of this permafrost melting, and then we're going to go into an unbelievable warming. We're going to be growing tropical trees here like we did 70 million years ago. So for years, methane was going up, and then it leveled out. Look at that. And then it started going up, and now it's really going up fast. And if you can figure out this, there's probably another Nobel Prize in this, if you can really figure this all out. But what we're finding, a lot of people thought that this methane was from fossil fuel production, from drilling, from leaking pipelines and stuff. But we can look at the isotopic signature. Methane that was made when coal and oil and gas was made 70, 100 million years ago has a different isotopic composition than if it comes from decay. Almost all of this is coming from the decay of vegetation in the Amazon basin. That's hard to believe, but in the spring and summer you get heavy rain. Now that climate change is warming up, you're getting heavier rain in the Amazon basin, you're getting more water, you're getting more tree leaves going in, and the methane is going up. This is another feedback mechanism that nobody had really thought about until about the last 10 years, and now we're seeing this happen. How can we tell this? Because we've got stations all along different latitudes, and then you can see the different latitudes as the methane moves up after the summer. You can just see the peak moving to the north. It's not coming from the oil and gas and moving south yet, or the permafrost melting, but it's going to be coming. Now, if you take all of these gases together, these are the three that cause the global warming: carbon dioxide, methane, N2O. Here's years, this is 2020 here, and let's go back. Let's worry about this later. Let's talk. You can see that methane and all these things were fairly stable for the last 2,000 years. So you say, oh, Schnell, how the hell can you measure something 2,000 years ago? Really easy. You look at ice cores. And when an ice core in the snow is formed, it captures air in little bubbles in that and freezes it in there. And then more ice on top, more ice on top. So you just drill down, take a slice of that, melt it, and there you have the concentrations of the gases that were there. Pretty neat, eh?
Yes.
Yeah. But now, look over here. What started to happen in the late 1800s when you had the Industrial Revolution coming in. All of a sudden, everything started going up. Carbon dioxide, methane, N2O. And on that scale, it's almost totally vertical. Those concentrations now are much, much higher than they've been for 1 million years. 1 million years, that's a long time. And how do we know that? Again, from ice cores that have been made. Now look at this. This takes a little while to catch on. This is a skipping rope. This is the South Pole. This is Mauna Loa, Hawaii. These are all of the station measurements by years. See them over there, 202, 203. And this is the CO2. It's all coming from the northern hemisphere where all of the big lumps are. Oh. Now, let's run through this again. It should work. Bear with me a second. It's a neat graph once you figure it out.
There we go.
Yeah. You see how in the northern hemisphere, there's not as many stations. You'll see more dots come as we get more and more stations. Mauna Loa is kind of the world CO2 average. So see them keep going up, and see the map over there where more and more measurements. And then you put them all together, and you have this big curve here. Now watch. Now we're going to go back almost 1 million years. Okay, and this is the CO2, the highest it's been in 800,000 years. Okay, let's watch it one more time. All the gas, oil, coal that we're burning is going in the atmosphere and it's staying there. We call this the skipping rope, but the northern hemisphere is running it. Now I'm going to stop it at a certain point. Right up to 2022. Okay, now let's watch farther back. 1960, now year 800, 50 years. Now we're going back, and we'll stop it at there. Oh, these are all of the different groups in the world that contribute this data to us. Now you say, okay, the CO2 is going up, the methane is going up, but what's the big deal? Okay, the big deal is that temperatures are rising. There's absolutely no discussion about that. There's millions and millions of data points in there to make those measurements. Arctic sea ice is shrinking. It's going down really fast. The Arctic ice forms in the winter, and then in the summer and spring it melts back to a certain level and stops. And the bears move with it. They stay on the ice because that's how they eat. Sea levels are rising. Kiss Miami goodbye in 100 years.
Yeah.
Places like that. And polar bears are really missing the ice. A lot of them are dying. But polar bears used to be on land. About 1 million years ago, they were grizzly bears in northern Russia and Canada. They're coming back. They're now interbreeding. The polar bears are coming onto the coast and interbreeding and starting to readapt as the grizzly bears and brown bears do. And this is a cross between, I don't know if it's a female polar bear or a male, but anywhere, and they're big and heavy. Look at them. So they're coming back to where they used to be, but I don't know how long that can last because there's not that much food on the land compared to a seal. A seal has a lot of energy. When they catch a seal, there's a lot of good fat to eat there. It takes a lot of wild geese for them to catch, and that's what they live off, is the geese that you see flying around here. Some of them, their relatives were up in Canada, or up in Arctic Canada, and they got eaten by the bears. The bears have learned now to hunt geese because the geese molt and they can't fly when they're laying, so they can go in and eat them. In Alberta, most of you have seen the Athabasca Glacier. That's what it looked like in 1918. Look at it in 2011. Glaciers are receding because of the warm air, and they're receding fast. Now, the glaciers on land don't really affect sea level. It's like a person who would go pee on the ocean. It'd make you feel good, but the ocean wouldn't know it. The ocean is only getting bigger from the ice melting in Greenland and Antarctica. And the ice in Greenland is 2 miles thick. Think about that. That's a lot of ice. And as it's warming, it's slowly moving out on glaciers. But the biggest place where there's a lot of ice is Antarctica. And a lot of that ice is floating, and there's huge glaciers coming out there. And when you fly over it, it's pretty amazing to see all of that. I've been to the South Pole a few times because I used to be the director of that observatory. You can all go see that in Canada. Now, a bigger issue. Glaciers in the Himalaya Mountains. Over 1 billion people trust the water from the glaciers. The Ganges, the Brahmaputra, the Indus rivers are all coming from glaciers in the Himalayas. And now the farmers are loving it, but even too much. You know those big floods they just had in Pakistan? Part of that is because the rivers are flooding, but also the monsoon is dropping more water. But the farmers love it because they're getting more water now for irrigation than they've had for a long time. It's great. The tap is running full, but one day what's going to happen? The tap's going to stop. And there's going to be 1 billion or more people one year, their crops are not going to have any water. The year before they had so much water, it was heaven. Next year the glaciers finish. So that's a big issue. Politically, can you imagine when that happens, the turmoil that's going to be in those countries? It's already starting a little bit with all that water stopping. You know, they were trusting it, and goodbye. Now here's an interesting thing. This comes from the Yamal gas field in Russia. A friend of mine who I work with in Russia a lot, he's an American, but we worked a lot in Russia for many years. This is a big blowout in the permafrost. See the size of the man up there? Mm-hmm. And this permafrost is starting to melt. And the methane that's in there is building up into, you can see big pimples. But this one caught fire. Somehow a little spark on a piece of flint or something. That hole is 180 feet deep. And you can notice there's no detritus around. It blew it at least 200 to 500 feet away when it exploded. My friend pictured 12 of these as they flew over going up to the Arctic. So something is really starting to destabilize methane in the Russian Arctic. This is one of the biggest gas fields. This is where most of Europe was getting their gas, is from the Yamal field, because there's a lot of methane down deeper. So this is a real interesting phenomenon. No one has ever taken a picture yet of this happening, but I'm sure that somebody will have a camera set up and wait for the next one to blow. But that probably indicates the instability in the Arctic and the methane. And remember, there's more methane in the permafrost than there is in all the oil, gas, and coal that we've ever had on the Earth or still have there. So if that really ever kicks in, our descendants, many, many generations from now, will enjoy tropical trees as they are here. I was just driving around Alberta the last few days, and I've noticed corn all over the place, especially in the east and south. People are growing corn, big fields of it, that 20 years ago, they'd call you crazy if you could plant corn. And now the climate is warm enough and the seeds are getting better enough. It's changing agriculture. The standing corn, farmers just turn their cattle in. The cattle eat the corn. They don't have to feed them. They can stay there till Christmas or more. And they're self-feeding. It's really neat how it's changing agriculture in that respect. But anyway, I've been telling you about scary and bad things. Let's look at a couple good things. Oh, good. You've all heard about the Montreal Protocol, haven't you? Those were gases, 4 gases that mankind made. Those are the species there, CFC 11, 12, and they were all in air conditioning. Remember, your cars used to have one type of, and now you have to put a different one in if you've got a really old car. I have all my old cars. My youngest car is 23 years old. My oldest one is 40. I went to put Freon in the old truck. I couldn't buy it. Aha, you can buy it on the black market, and it's cheap. Seriously. So I just bought a couple of canisters and put it in. Don't tell the government that. But I only did it once. Okay, so the Montreal Protocol came in. All the countries of the world signed it, and look what happened. The gases all started to go down, which really is a good story, isn't it? And the ozone hole is still there. It's still big, but it's the drivers of it, the fluorocarbons and others, are getting less and less. But remember, we have these stations all over the world. And if everybody in China ate beans, we could tell you how much. Well, somebody in China or somewhere over there was starting to produce CFC, or 11. We could detect it. At Hawaii, we could detect extra molecules coming that shouldn't be there. Right in here. The curve should have been going down like this. Aha, it's going back up. Somebody is cheating. Well, from Hawaii, we could narrow it in to somewhere in China. Remember, we can measure one molecule, and we measure it now. I told you about 1 part per trillion. We're now measuring in 1/100 part per trillion. And that takes really good instruments and really good people to do that. Very fine. But, okay, how are we going to figure out where in China this is coming from? Well, we have some friends in Korea. They have a station. So we put up measurements at Anmyeon-do. It's a little island off Korea. And we do air trajectories, which means that we look at air that comes, and using maps, we can tell where that air has been a week ago, a month ago, or days ago. We can tell exactly where it comes, and you can see the pattern. But when the air came from certain areas like this, no cheating in it, no CFC 11. But when it came over southeast China, a certain town in southeast China, boom, there was the molecules. And we narrowed it down to one city, and then some other people went there and talked to different people, and they found a factory that was making foam for refrigerators. One factory making foam for refrigerators was changing the world's. And they were doing it illegally, of course. And when people talked to them, they said, well, we did it because the new chemicals that we had to farm are so expensive now, it's much cheaper just to go back to these old ones, which they were doing. I assume that China, and then the good story is, we told the UN and we told the Chinese government, and the Chinese government believed it immediately, because they asked their scientists, is this data any good? And their scientists said yes, because we've been watching. They let everybody know exactly what it's doing. We trust them, and immediately the Chinese government went and stopped it. We assume they executed the people. That's probably what they do. No, don't laugh. They're really hard. Don't cheat in China. But anyway, it stopped. Within a week, you could start seeing it going down. But since then, somebody else is cheating now. And it's somewhere in Asia, and it's not that part of China. It could be Vietnam or something. So we're going to have to, or I should say, I'm not working there anymore. I retired last week. But we'll probably put a station somewhere downwind of Thailand on a ship or something and see where that's coming from. Now, how will global warming affect Alberta? We don't really care about the rest of the world. Let's just talk about things that worry us.
Our backyard.
Our backyard, yes.
And front.
Well, you've all seen the temperature change. The temperature's going to change a little bit. It's not going to be like this every year, but there's going to be bigger variability. But over time, there's going to be more events like this where it's warmer in the fall. You're going to have a lot fewer spring frosts. You know, spring frost, if it's maybe 10 weeks or 10 days earlier than it should be or something, it's going to affect crops. But if you take that one frost away in the spring, you can imagine how much better the plants are going to be in the crop. And the same in the fall. If you just lose that one big freezing event in the fall, you're going to get, what, a week, 10 days, more growth, or even more. And that's really going to make a difference, especially if you get one in the spring and one in the fall. Now you've got a whole month of growing season that you're not going to lose your Saskatoons to blossom, to frost, and in the fall you're not going to, your crop is going to, you're going to get your crop off before it freezes. So that's good. There'll be bigger swings in climate. Now, I forgot to tell you, and let's go back to this globe. CO2 mixes around the world. So in the equator then, which gets more sunlight, it gets warmer down here than it does in the Arctic, obviously. So all a hurricane is a bunch of high energy from the equator moving north to balance the equation. because the Arctic isn't going to get colder. And in the winter, all of a big cold front is the same thing. You got too much cold air up there, you got to balance the bank account. And over the space of a couple of years, it comes out almost to zero. So you're going to get more hurricanes or more intense hurricanes because you got more energy moving north. Occasionally, you're going to get hellish, hard, cold winter for a week or two as the cold front comes down, because it's got to get that cold air out of the Arctic. It's got to get it down to the, and it's going to go all the way down to Florida and freeze the oranges in the middle of winter. That's happening occasionally. So you're going to get these extremes. You know, you're going to have climate warming, but there's going to be times when you're freezing your butt off and wondering where's the climate warming, because all this cold air is coming down to balance the equation. But overall, it'll only be a few degrees warmer, but the amount of energy that you have in a few degrees is amazing when you think about it. And most of the heat is not going onto the land, it's going into the oceans, because they're 70%. Look at all of the ocean you have down there. And the ocean has currents. The ocean is not static. There's areas where it heats up and then the currents move and they go around and they come around. Up in the Arctic, the current goes around clockwise and then it goes down the east side of Greenland and takes icebergs down to St. John's, Newfoundland. I'm sure you've all seen pictures east of St. John, a big iceberg looking out there. That was up, coming down this way. You have other ocean currents like the Gulf Stream that generates heat here, comes up here, goes around, and then off, and then it comes up, and it goes over here. You can grow bamboo on the west coast of Norway. Think of that. And you come across where that is. That's beyond the Canadian islands. North of the Canadian islands, they're growing bamboo because of the warm current coming out. And then that current sinks. It goes right down, and then it goes under the ocean again. And there's other currents like that. There's a current off Japan, the Kuroshio current. Takes heat up here. That's why Japan is quite nice. You come around, it's in the middle of Siberia. That latitude over here, that latitude's in the middle of the US. So these currents, right now, there's a lot of warm water sinking in the ocean in different currents. And it may come back in 10 years, it may come back in 100. And once it gets under the water, it doesn't go away. You don't lose the energy. It doesn't disappear. It stays there in the water. So these currents are moving around slow, and then they all come to the surface somewhere. Some of them are coming to the surface around the Antarctic ice shelf. And you've heard of, there's a big ice shelf that they're worried about now that's going to melt, because this warm water is coming, and it's slowly eroding underneath, and there's mountains holding this, but once you get that eroded, the whole sheet's going to come off. Huge amounts of ice. So there's this big latent amount of heat that's under the oceans and in the oceans that's going to come up somewhere, someday. It may be 100 years, it may be 1,000, but it's going to come back up and affect the climate too. So back to what's in Alberta. You're going to have climate norms changing. You're going to have hotter summers, drier summers. You're going to have wetter summers. You're going to think, man, this is great, a lot of good water. And then next year it'll be dry, because it's going to, it takes a long time for the Earth to balance this, because there's a lot of inputs and a lot of outputs. It's like having a bigger bank account with 20 of your kids and cousins and other people putting money in and taking money out. It's just coming and going all the time, but eventually you've got to balance it out. Also, forest fires. Alberta has a lot of forest. You're going to see a lot more forest fires some years, because the forests on good wet years grow, and then in dry years they get a little tinder, and then you get a lightning storm, you get a west wind, and there goes your oil sands town. I'm on a government commission that meets twice a year, and they ask us all kinds of questions, and we met up in the oil sands just the year after the fire. And then we met again up there just the year after the big flood. So they're getting it from both ends. They're getting the fire on the west side and the flood down below. And that's all driven by changes in the normal balance of the climate. And it doesn't take much to have the ice back up, or for storms and fires to get started and move along. Corn. I'm so amazed on all of the fields of corn I see here. When I was a kid, you had a hard time eating corn in your garden. And now I see acres and whole sections of corn. And that's because the seed's better, but also the climate is a little bit different. And that's just enough to keep the corn growing. What can we do about that? What can we do about climate change? A lot of things we could do, but are we going to do them? Reduce, eliminate fossil fuel consumption. First of all, how are you going to do that? And secondly, wouldn't that affect Alberta a lot? So there's a lot of pressure in some countries to completely get rid of fossil fuels. I don't see that yet here, but keep that in the back of your mind. Politically, it's a pretty big question. We could shift to solar, wind, and especially nuclear. Because in Alberta, you don't have much solar after November through to March. And wind is okay, but you've got to have an awful lot of those towers and all of those towels to make snow. Nuclear is really the answer. But again, there's a lot of difficulty in people's mind about nuclear. We should have smaller, more powerful nuclear plants instead of the big, huge ones that people have been making and take 10 or 20 years to design and build. If you had smaller ones, say one for central Alberta or one for Red Deer even, just a smaller little unit that you could use your electricity, that would be an answer. And politically, it's not easy to even suggest these things, but socially and economically, you're probably going to have to do that at some time. And the Canadian government is starting to look into building and thinking of what it would take to make a small can-do reactor instead of the big ones that they have. Switch transportation and heating to electrical. Those are two big uses of fossil fuel, really big uses. How many of you eat fresh fruit in winter? Yeah. Where does that come from? Either a greenhouse or South America or somewhere down in South America. It gets flowing up. Transportation uses a huge amount of fossil fuel. When you drive down the highway, all those big trucks moving, whatever they're moving, concrete, oil, cement, cattle, something, they use a lot. They get, how many miles to gallons does a big truck get? 2 or 3? Or is it a mile per gallon? I don't know, but it's huge. That's all going to have to change if we're going to protect the climate. We've got about 5 years before things really get bad, or maybe 10. But once the climate change kicks in, remember, carbon dioxide stays in the atmosphere 100 years, 1,000 years. So that blanket is there. If we stopped carbon dioxide today, totally, we'd still have 100 years of warming. Think about that. Because it's out there and the feathers are still in the bed. Now, the biggest issue, and this is something politics don't even talk about, is population and consumption. We have 4 billion too many people on Earth, basically. And I first went to China just after Mao died. I married a Chinese, so that helped us get in. And I met a lot of scientists and people, and they were, eminent scientists were living in an apartment building, sharing a kitchen, sharing a bathroom with 3 or 4 other families. And these were really eminent scientists. I've gone back to China every few years. One friend I've had for about 40 years, he lives in about a 3,000 square foot house now, marble floors, 2 kitchens, a whole wall screen, 2 servants, same guy, remember, in China. Their living standards are incredible. I don't know how many of you have ever been to China, I'm sure some of you have, but I was in Beijing once and I had a morning off, and I went out and I counted 500 building cranes, and that's before lunch, and then I stopped counting. They were all building high-rise apartments and high-rise buildings. It's incredible. Shanghai puts New York to shame with all the beautiful buildings and stuff. And they've raised the living standard of 500 million people from starvation to modern levels. But that takes a lot of consumption of energy. And a lot of their energy is coal energy. And they're burning a lot of coal. And now they're getting Russian gas and oil cheap, so they're burning a lot of that. But as rich countries, we've got to think about what we're going to do. I live in a house that has 5 bedrooms. I sure don't need 5 bedrooms. I could put other people in there or live less. But it just happens that I bought that house years ago when it was cheap and easy. And our lifestyle is so different and so consumption. And we have cars, a lot of cars. When I first used to go to China, I would ask a group of, say, 200 audience, how many of you have a personal car? Not a hand would go up. And then somebody would say, well, our commune has a bus. Now I go there and ask that, how many of you have a car? Every hand goes up. How many of you got 2 cars? Maybe a quarter of the hands. How many of you got 3? A few. All their kids got cars. They're consuming. They can afford it. How can they afford it? All of the made in China goods. I bet you half of what I'm wearing is made in China. My shoes, my pants, my jacket, my watch, all made in China. And that's money that spreads around. Okay, I'm going to shut off the basic science now, but I want you to look at the next thing. Has anybody figured out what that is?
Carbon.
What?
Carbon.
Kind of, but what?
Oh.
What made that?
CO2. Oh.
What made that? It's a fossil, you're right. Remember, they come in many different sizes. I just let you see a little one. Here's a 20-pounder. If I can lift it, they're 30 pounds. That's fossil worm poo. Think about that. It's 70 million years old, and it's only found in 2 places in the world. Little ones like the one I passed around in Japan, and the big ones like this in one area near Castor that is about 100 meters wide. 2 places in the world. And when I was a kid, we would go out and play in this really sharp valley, and when you walked through the creek, the only places you could cross the creek is where there was bedrock came to the surface. Otherwise, you know, when you try to walk through a dugout or slough, what do? You step in mud up to your crotch, right?
Yeah.
Well, the same in a creek. But where we could cross the creek, there was rocks there, and when you walk, you could feel these round rocks under the water. So I took one of them home and kept it at my parents' house for 50 years, and when they died, I found it, and I decided to find out, what is this thing? So I looked at it, and when we were kids, we would go out and have wiener roasts out here and stuff, and strip down and swim, and behind the beaver dams, we wouldn't really swim. You'd go and freeze your butt off and then get out of the water. But we looked at these things and said, those have to be petrified buffalo hearts, aren't they? And remember, we're 8-year-old kids. And then the other kids who were a little older, where did that small one end up? Somebody said, oh, that's a fossilized turnip. And then one of the older boys says, oh, no, that's a fossilized maiden breast. But we didn't know any. Indian breast. We didn't know any different, you know. So years later, I contacted the Tyrrell Museum and sent them a picture, not of this one here, but of one like this without the prop. And they said, oh, that's just a natural feature. Don't bother us. But I didn't accept that. At that time, I knew it wasn't the buffalo heart or anything else. I thought it was maybe a stalagmite at the bottom of a cave with water dripping down on it. So I convinced the head of Tyrrell to send one of his scientists up to Castor one weekend, and we got together all my old friends, and we took him out and showed them these things, and he couldn't figure it out. And then he asked, well, that's all the ones we found in the bottom of the creek. He asked, is there any of those in the walls anywhere? And we, you know, we're talking about 80, 100-foot solid straight walls of sandstone and alkaline soil. So we found one area, and he found some of these in the old seashore, and they were pointed up this way, they were pointed up this way, actually like this, and they had a big, you can see the point up there. And then he figured out what it was, or told us what they found in Japan. there's a worm called a Rossiella worm, and it used to live in the seafloor, in the mud, right at the edge of the coast. And this is the worm here. And then it would put out tentacles, and when some food came by, it'd grab the tentacle, go down into the mud, and digest it. Okay, once you digest, you got poo, right? So what do you do with it? The worm would push it out. You see, pushed it out there, and he'd go down deeper and stuff. And over the years, he'd build this big pile of shit, basically, packed in there hard. Then what happened? A freshwater stream came just in this one area and brought iron in it. And so the iron went into the poo and fossilized it and turned it into solid iron rock. And it's only in this area is about 100 yards where the base of gravel or the base rock comes to the surface, and the stream has gone over there, and then these things fall out of the side of the cliff, and they hit this base rock, and they can't go anywhere. There's probably lots of them on both areas, left and right of this certain area where we found them as kids. But of course, they're so heavy, they just keep going into the mud, and then they're down somewhere down in there. So we then found out that there was a professor in the University of Alberta who studied these things in Japan. So I'm taking that up to him next week because the ones he's ever seen are much smaller than the ones I just handed around. He's never seen one like this. And they come bigger, I just couldn't carry it out. It took me about an hour to move a mile in the valley, so narrow, and all of the pine trees have fallen into it. The creek is only 3 feet wide or 4 feet wide, where it goes through where the rocks are. So it's really hard to get in there now and to find these. We've probably picked up most of them anyway. So with that, I will thank you all for your valuable time, and I'll be open to any questions you want, sociological, financial, scientific. I do that in high school. Oh, you see some of the questions you get. When did you first have sex? First question, always. Feel free to ask any questions, sir.
I've been listening to the news around the radio, and 70 years ago, we talked about removing CO2 from the atmosphere, not pumping it into the ground, nothing like that, just removing it, much like they remove nitrogen. They put nitrogen using the oil field. Now, what's your take on that?
He's asking about removing CO2 from the air. It can be done. It can be done a number of ways, but it takes more energy to do it.
Yeah.
It doesn't pay off. You're putting out more CO2 than you're taking out presently. Now, if you can use hydrogen from the ocean or use solar energy and get enough of it, yes, that will work. But it's expensive to build these things, and you'd have to have an awful lot of them to suck out the CO2, because just down the road, somebody is putting out more CO2 than you're taking out. That would be ideal, and a lot of people are trying to think of ways to do that. There might just be a way. If there was, that would be fantastic. They would just suck all the CO2 out, problem solved, maybe.
So if we sucked it out, where are we putting it?
Pardon?
If we take it out of the air, where are we putting it? In the ground?
In the ground, or put it into, you can make it concrete out of it. You can do a lot of things with it once you get it solid, yeah. Putting it into the ground, there are places putting it into the ground now, especially Norway. Oh, Norway's a strange and interesting country. They produce a huge amount of oil, the North Sea. They don't use any oil. All of their cars, all of their heating in their buildings, all of their transportation is electrical. They do it from all of the hydroelectric. They even have lines going 30 miles out into the ocean to little islands. Electrical. They have the most electrical cars anywhere in the world per capita is in Norway. But they sell millions of barrels of oil a day. So I wonder how their conscience lasts. This lady and then you. Okay.
Yes, I'm wondering if you or your colleagues have a theory about why the Arctic is warming faster than 2 to 3 times faster than everything.
Yeah, the Arctic is warming about 2 or 3 times faster than the rest of the world. The reason is that low-level clouds in the Arctic used to have just water in them. But now some of them are getting ice crystals in the lower part. Normally, when you have a cloud, the ice crystals form where it's much colder on top and move down. In the Arctic, ice crystals are working in the bottom. And the ice crystals act just like CO2. They hold the heat or they reflect the heat back down. And there's an interesting story that relates back to red deer and pinhole. The little particles that are probably causing this are made by organic material, plankton in the oceans, bacteria in the oceans. This is something that I discovered at Penhold in 1968, that bacteria make little ice nuclei that cause rain. And in the Arctic, it looks like the plankton is making this, and now that the Arctic ice is starting to melt, there's more plankton, and it's putting it up, and so they're making ice crystals in the bottom of the clouds, not the top. And that's probably why it's heating. And there was just a huge multi-year program where they took a big icebreaker up and froze it into the air and had hundreds of scientists studying all of this. And they're starting to publish papers now, and we'll know more about that. I used to be the director of a program where we flew a huge plane across the Arctic all the time, measuring all these other things. But that program ended in about 1991. But if we went back, we'd be able to see those changes now. You were next, and then over there next.
Back to the worm poop.
Uh-huh.
Now you said that that worm would collect, or iron would get down into the worm poop over time, with fresh water?
Yeah.
Like that. So would it be incorrect in saying that that worm poop now is iron ore?
It's not very magnetic, though. That's the first thing I did, was put a magnet on it, and it wasn't very magnetic. So it's some kind of an iron chelate or something. But it's not enough iron ore to melt to make anything. Lady in the back? No, at the back, and then you in the front.
You were talking about more plankton forming as the ice melts.
Yes.
And somewhere, my husband heard on the, I think on the television, something about a scientist who believes that this global warming is actually greening the earth.
In some places, yeah. You're getting more vegetation, especially in the Amazon basin. But greening is a very relative term. If you're greening crops, you harvest the crop, feed it to cows, or eat it yourself. If it's in trees, give it a few years, it's going to fall down or it's going to burn. So putting any carbon dioxide into vegetation, trees and stuff like that is a very short-term saving of the atmosphere. And since population is growing more, we're reducing forest areas, especially in Brazil. They're cutting down the forests so that they can put farmland in or cattle ranches. So assuming that we could take the CO2 out by vegetation is not a long-term prospect. But in the short term, yeah, look at how good the crops were this year. There's a lot of CO2 got sucked out, but it's all going back, in the next year or two. This lady and then you.
So prosperity requires more consumption,
Yeah.
and more consumption requires more people.
Yeah. Well, no, the people, each person consumes more.
Each person consumes more, but then more people consume
Yeah.
more.
It just keeps getting bigger.
So to have prosperity, we need more consumption and more people. So how are we going to reduce consumption and reduce the world's population by 4 billion?
I don't have an answer to that. It's just a possibility. I can say these things, but I have no power to initiate any of it. But, there's going to be huge disruptions in population movement once, let's say, Pakistan doesn't have any more water. Where are they going to move to? No, there's not enough ships. They're not going to make it across the ocean. They're going to move into India. But India's got the same problem. So they're probably going to die. Let's be realistic here. You're going to see huge population reduction sometime in the next 100 to 200 years.
California, the south is going to have to come up, have to move north.
Yeah, and Florida. Okay, there was one other lady I pointed to.
Alberta's water source, are we predominant snow melt or
Where?
in Alberta? What do we rely on for our water?
On water, mostly rain. There's irrigation in the southern part, and the cities use the rivers for water, but mostly it's rain. But of course, the rivers that come out of the mountains have sources in the glaciers.
Because I was in the, like this summer, I don't think I've ever seen the mountains without snow,
Yeah,
without any snow.
yeah, and
In
you're gonna
September, there was no snow.
you're gonna see more of that. The rivers are gonna get lower and less. There was one person there, and then you. Okay.
Can you comment on the notion of DNA being spread in the air?
DNA? Yes, it can, but it depends. It has to have it can spread by bacteria. It has to have some viable form. Seeds can take it, but it's not really something that humans are too concerned with.
So we understand what's happening, this future and everything like that. In your opinion, do you feel us, as mankind, can adapt, continue to live, or
Die out. He's asking my opinion of the future of mankind. I think, yeah, mankind will survive, but it'll be in a different format and probably not exactly where presently we live. As it gets warmer, populations are going to move. Alberta is going to be much more pleasant, and Russia is going to be far more pleasant. A lot of the tropics are going to be non-existent. Some of the islands in the Pacific are not going to exist. I'll tell you a story. About 20 years ago, I had a man from Kiribati, the Prime Minister of Kiribati came to visit me by accident and a different reason. And he asked me, he said, what can we do for our island? And I jokingly said, oh, you've got to get some country to give you land, ha ha ha. Because it's just a small island, it's only a couple feet above sea level. 8 years later, he was in Australia, and Australia said, we will give your population land if it does. And there are actually people moving now from Kiribati to Australia. But that's just, they've only got, what, 3,000 or 4,000 people in their country. So it's a small problem in a big country. But you're going to see more of that. But the disruption, I can't predict really where it's all going to go, you know.
What's your opinion? Oh, sorry.
I had a question incoming from Pastor, but they haven't typed it yet.
Oh, okay.
What's your opinion on the race to space versus time on the planet?
Oh, why would we spend billions of dollars to fly one or two people to another place when we could take half of that money and change our agriculture and build housing for people?
Back to business.
I talk to NASA people occasionally, and you know, it's something mankind has to do. Hell no, you got to keep your people here living and keep things here. So I know the head of NASA because he was my guest once at Mauna Loa Observatory. I had him for a whole day, and he's a great person, but he controls billions of dollar budget, and they want to go to the moon. They're going back to the moon. They're going to go to Mars. They're going to cost $1 billion per head to get there, but it doesn't make sense, does it? And somewhere over here. Oh, this lady, and then you.
Yeah, I was just wondering about the patterns of warming and cooling in history. Thinking of the hypsothermal event in the Holocene period, and Earth came out of that. Number one, I'm wondering what caused that. I know there was the eruption of Mount, what was it, Mazama? But Earth came out of that, and then it became very inhabitable again. Do you see that same pattern could happen?
Oh yes, she's asking about how climate change and different things that do it. We've had at least 4 complete ice ages where the Earth was just a hunk of ice, and also when it went tropical. Around Castor, you can find all kinds of fossil wood and big trees that grew, you know, tropical trees 3 feet across. That's pretty amazing. And just yesterday I took somebody from the Castor Museum and took them to a tree that's about, well, let's say 12 feet long, 3 feet wide, that they're going to put in the museum. It's 100 million years old, So this area was all tropical once, and it's gonna be tropical again, and then it's gonna eventually probably go into an ice age maybe. But first it's gonna go tropical.
I've got the questions from Castor. The first one is a bit of a review question. Excuse me. Can Ross explain exactly how carbon dioxide traps the sun's heat in the atmosphere?
Okay, the molecule of CO2 is just like a feather. It holds heat. I can't explain the physics of it, but we can do really neat experiments. You can take a glass jar and shine a light through it, and then you can put CO2 in it, and the whole heat just goes, it'll go up 20 degrees just by shining the light through, because the molecules hold the heat just like feathers. I can't explain the physics of it, but I accept that it's true.
And the second question is, our water comes from the Red Deer River. How long till it dries up?
It depends how much they store in that dam out at.
Yeah, the dam is what's saving our bacon right now because there's almost no water in the
Yeah,
Red Deer River.
they save it. I would say it'll never dry up because you'll always have rain, and you'll always have a bit of snow. But there'll be periods where the water will be pretty low. You know, I don't know how much they've got stored behind the dam, but the dam was put in just to solve that problem.
Right. Russ, we have really, really enjoyed an opportunity to learn about climate change. And we could go on here all afternoon.
Yeah.
But I'm going to say thank you from all of us, and we will express that appreciation to you. We'll break up, and you can answer questions individually to the people who would like to know further things. So a big thank you